So for today's deep dive, we're looking at something just incredible, the Mansourah enclosure in Tlemcen, Algeria.
It's this massive fortification. We're talking 12 meters high, built from rammed earth.
And it's been standing for, what, over 700 years now?
That's right. But the real problem isn't its age. It's that it sits in a pretty active seismic zone.
Right. So the question isn't just about its history, it's about physics. How does a massive earthen wall like that handle a modern earthquake?
And that is the core of the problem. You have this culturally protected site. You can't just, go drill a bunch of holes in it to see how strong it is.
You'd end up destroying the very thing you're trying to figure out how to save.
Exactly. How do you know if it can survive a big one without, well, breaking it?
Which is what makes this 2026 study by Hanini Walid and Bamekra Nadir so interesting. They figured out a way to bypass that physical risk entirely.
They built a digital twin. They used a program, ANSYS Workbench, to build a perfect 3D model.
So they decided to stress test history inside a computer without touching a single clod of actual Earth.
It's really the only way to do it safely. But for a simulation like that to be accurate, the data you put in has to be flawless.
You have to tell the computer exactly what rammed Earth is.
And this material is surprisingly sophisticated. We think of it as just packed dirt, but it's not.
The study actually did a mineralogical analysis. I saw that it's almost half calcite and quartz.
47%, yeah. It's basically a natural high-performance composite. But the most telling result came from the methylene blue test.
Okay, what does that tell us?
It measures how reactive the clay is to water, and the value they got was under 0.1, which is, that's the gold standard.
So it's almost completely insensitive to water. It's not going to swell up and turn to mush every time it rains.
Which explains how it survived 7 centuries of weather. It acts more like a stable geopolymer than, backyard mud.
That structural integrity is key. But modeling how that material actually moves during a quake, that's another story.
Right. That's where the math gets really specific. You can't use a standard engineering model like von Mises, which you'd use for steel.
Because steel is ductile. It stretches and it bends. Earth is granular. It relies on friction, right?
Precisely. It's all about the friction between individual particles. So they had to use the Drucker-Prager criterion.
Okay, break that down for us.
Imagine a pile of sand versus a steel beam. The beam holds together with atomic bonds. The sand pile holds its shape because of the friction between the grains. Drucker-Prager models that internal friction.
So it calculates the exact point when the particles stop gripping each other and start sliding apart?
The moment a crack forms. Yes.
So they fed this super detailed friction model into the computer, and then they hit it with 2 different seismic signals.
They did. First, an artificial signal tailored to Tlemcen's current building codes, but then they upped the ante.
They used the real thing, the actual recording of the 2003 Boumerdez earthquake.
That's the nightmare scenario, a magnitude 6.8 event. And running that waveform through the digital twin showed something fascinating about how the walls behave.
The modal analysis, yeah. It showed how the wall dance, I think is the word you used.
It is. At lower frequencies, the walls just kind of slide side to side, a simple horizontal translation.
But when the shaking gets faster,
they start to twist. You get this torsion effect, which is absolutely deadly for masonry structures. The corners, the towers, they amplify that twisting.
But the study also factored something in called Rayleigh damping.
Yes, and this is crucial. They estimated it at about 4%. That's the Earth material itself absorbing and dissipating the energy of the quake.
It's not just rigidly shaking, it's actually soaking up some of the shock. That might be the secret weapon of rammed Earth.
It's a huge factor.
Yeah.
And the simulation successfully identified these very specific critical damage zones where stress would spike beyond what the material could handle.
So it's like a heat map for conservators. They now know exactly where to go to reinforce the walls before a quake even happens.
It's predictive conservation. You're fixing the failure point before the failure. It totally changes the game for protecting heritage sites.
It makes you wonder, though. If this 14th century mix of dirt is waterproof, has high thermal inertia, and provides its own seismic damping, why are we so obsessed with concrete?
That is the provocative thought, isn't it? We might be looking at a 700-year-old blueprint for sustainable, high-tech construction for our own cities.
Maybe the smartest building material was right under our feet the whole time. Thanks for listening to this deep dive. If you want to see those stress maps for yourself, go check out the full study.